Hey guys, how's it going? Welcome back to FizzWiz. I'm Manas Sharma, and in this tutorial, I'll be showing you guys how to train a NequIP machine learning model from scratch to predict energies and forces on complex chemical systems. Now, before we get started with this tutorial, I would like to strongly request you guys to subscribe to my channel, and you can find it on YouTube by the name of FizzWiz. And I usually create a lot of tutorials on computational material science, scientific computing, and so on. And it would really mean a lot to me if you could subscribe to me and show me some love. Also follow me on Twitter to get more updates whenever I upload a new YouTube video. So thank you for subscribing to me. So yeah, so this NequIP paper actually came out in 2022 in Nature Communications, and it basically changed the game of machine learning models for chemical systems. So I'll put a link to this paper in the description down below, and I'll also put a link to the GitHub repository for the NequIP code in the description down below. So what is NequIP? So NequIP basically stands for Neural Equivariant Interatomic Potentials. Now, if you are slightly familiar with machine learning, then you already know what neural networks mean. So that's where the neural term comes from. And then the equivariant term I'll explain in a few moments later. And then the interatomic potential basically means that it is meant for chemical systems and predicting the energies and forces by learning the interatomic potentials of those chemical systems. So it can be used for performing molecular dynamics of really large systems very quickly. So what does one usually expect from a good machine learning model? So of course we expect it to be accurate as the training data. So usually we train our models on DFT data. So that is why we would expect it to be at least DFT accurate. Then it should also respect the 3D symmetries of these systems. And what I mean by that is, for example, let's consider this. So the energy predictions should remain constant across various transformations such as translation, rotation, reflection, and so on. And what does that mean? So what that means is it can be explained very well by looking at this water molecule. So let's say this water molecule has some energy X. Now, the fact that I rotate it like this should not affect its energy. I mean, it's just that isolated water molecule. So its energy should remain X. So this is what I mean by the energy should remain invariant or respect the symmetry. Similarly, if I translate the water molecule like this or this, the energies should remain the same, right? And similarly, talking about the equivariant forces, so what we want a model to predict is that the forces should be equivariant. Now that can again be understood by looking at this water molecule. So let's say this hydrogen atom currently experiences a force along the this axis towards the O atom. Now, just because I rotate it like this shouldn't mean that my force remains the same like this, but the prediction should also follow the input. So it should change correspondingly. So that is what is meant by equivariant forces, that your forces also respect the symmetries and change accordingly. And then the model should be size extensive. What that means is that you can train it on a smaller sized data. Let's say you train it on a system with 100 atoms, but then you can still perform simulations for systems with thousands of atoms. And finally, it should be speedy and efficient, and not only efficient in terms of like computation time, but also efficient in terms of data set. So you shouldn't require like millions of data points to train your model, but it should perform really well even if you could train it with like thousands of data points only. And this is where NequIP comes into the picture. It basically does most of the things that I talked about earlier. So it is a message pass. The architecture that NequIP follows is that of a message passing graph neural network. So here the atoms are represented as nodes, and the pairs of atoms are represented by these lines or these edges. And the key advantage that NequIP has over has over the previously known message passing graph neural networks was that these atoms not only carried the scalar features, so that are denoted in red, but also they carried these vector features. So that would be like 3-element vector feature denoted in blue, and even tensor features. So what that meant was that you could now have a better description of your system, and then the convolution over the neighboring atoms was equivariant to transformations in 3D space. That is basically what I talked about earlier. So the features should change according to the input, and so should the output, that is the force. So here these lines essentially show the messages being passed iteratively, and here is sort of like a flowchart of how NequIP works. So essentially you specify your chemical system, then it maps the positions and species, and then it calculates the atomic potential energies and some step up to obtain the total energy, and then compute the forces as gradients of this total energy. And yeah, so um, a few more details you can also obtain from their own paper. So the figure 1 of their paper actually has a really nice flowchart covering essentially most of the details inner working of their model. It's really beyond the scope of this tutorial to discuss these in more detail. We will focus more on the practical aspect. So yeah, so in this tutorial we'll be training our model on the AIMD trajectories of a silicon crystal, a 2x2x2 supercell of the silicon crystal with 64 atoms. And this is the trajectory file in the XYZ format, or rather the extended XYZ format. So in the extended XYZ format, the first line indicates the number of atoms. Then you have 3 atomic positions for a given atomic species. And then you also have the 3 atomic forces for that particular species. And then you have multiple frames, as you can see. So that was the first frame. Now you have the second frame. In the first frame you can see that the forces are essentially 0, but then since this trajectory was for AIMD in the NVT ensemble at 800 Kelvin, so now the forces have increased significantly as you move further. And here is animation of this particular trajectory in JMOL, so you can see how the atoms are moving. And by the way, we have like 110 frames in our system, and that can be seen like this. So if I do this, so yeah, so you can see that I have 110 frames in this trajectory file. So that brings us to the main portion of this tutorial, that is how to train an NequIP model on this particular AIMD trajectory. Now to do that we'll use Kaggle.com. So there you can run your code online. You don't need a GPU on your computer. So you will go here, and maybe you'll need to create an account. So once you create an account, you can click on code, and then you can click on plus new notebook. And then I have already created an Kaggle notebook where I have all the instructions or the code to train a neural network. So I'll just import that over here. Yeah, so it's on my PC by this name. So what I'll do is I'll click on file, then I'll click on okay, so the import option is not coming up right now. Okay, it's still loading. Yeah, okay, so now it's loaded. Now I can click on the import option, and then drag and drop this Jupyter notebook, click on import, and I'll leave a link to this Jupyter notebook in the description down below so that you can download and then import it in Kaggle. So yeah, let's just wait for Kaggle to process it, and you can already see some of the code has been processed and it is showing up here. So let's just wait for it to be done. Okay, so it has been uploaded now, and you can see that I'm using the accelerator GPU P100, which is a really powerful GPU that you can get for free on Kaggle. So yeah, so first of all we'll install NequIP and Torch, and for this we'll use the PyPy Python package manager. So just click on one of these cells and hit Shift plus Enter. So this is how you will install something. So yeah, so Shift plus Enter. Okay, so now you can see it is being installed, and okay, so it's already installed now, and now we will check if we can import them or not by typing in import NequIP, import Torch, and then also printing out their versions. This will enable us to know whether the installation was successful or not, and indeed it was successful, as you can see right here. Then we will also check the current working directory. It's usually nice to know what you're working in. So we'll do print working directory, and since all of these commands that I've used here as well here are like terminal commands, So therefore I use an exclamation mark before them. If you use a Python command, then you don't need an exclamation mark. So you just click here and hit Shift plus Enter, and then is the main part. So the trajectory file that I showed you earlier, you can download it from this URL. So we'll do wget, again a command line utility, and then you can do ls to check whether this trajectory file was downloaded or not, and indeed it was. And here is the most important part. So here you will create the config YAML file for training your neural network. Now it has a tons of options, but I cannot of course cover each and every option in detail for this particular tutorial. So here we'll only go through some of the most important aspects. So the first important aspect is the root. So root would be the directory where your results get stored. So here I call it results, and then within that I create a subdirectory called SI. So this will be my root directory, and then within that you can also do like various runs. So yeah, so this will be my run name. So the run name can correspond to like where you want, like training 1, training 2, or you can also give it a more descriptive name as I have given here, that is train 80. So that means so the convention that I followed here is that I'll be training it on 80 frames, and then the validation will be performed on 20 frames, while the remaining 10 frames I'll use for testing. And then I'll be keeping the batch size 5 and the precision to double precision. I mean, this is not any parameters, just a name that I've given to my run. And then you have this seed. So be sure to always provide a seed so that your training runs are reproducible. And append should always be true in case you later on need to append more data in your model and like fine tune it further. And then as I mentioned, you can set the precision to be double or single precision depending on your needs. And then yeah, here is the most important part. So this basically talks about the parameters of your graph neural network. So as you can see, we had this particular circle over here, and that essentially gives you the radius within which the atoms will talk to other atoms or interact with other atoms, and that is given by this Rmax value. So here the radial cutoff is 4 angstroms in my case. You can also adjust it to higher or lower. A higher value will make your network really slow, so you'll have to optimize it. And the number of layers basically gives the number of interaction blocks, so that you can see in this flowchart in the NequIP paper. So the number of interaction blocks is given by num layers. And then Lmax basically gives the order of the features of your network. So if you have Lmax 0, then you only have scalar features. If you have Lmax 1, then you have scalar and vector features. If you have Lmax 2, then you have scalar, vector, and tensor features. Usually 1 or 2 are enough. If you go higher, then you will really make your network really slow. And then the parity, again, ideally should be true, because it will adjust your features based on reflections in the input. So it should ideally be true, but you can also get good results without it. So yeah. And then the number of features essentially will give you the size of your network. So usually 32 is a good number. You can even try 64 or 16 to optimize it, but yeah, 32 usually is fine. And then you can have some non-linearities. So this section will be about those that we won't really talk about much in this tutorial. Then again, radial network, we won't really talk about it much either. So that brings me to the next most important portion, that is the data set. So we'll be using the data set in a format that can be read by ASC. So that is why we specify the format to be ASC here. And then the file name is si-trajectory.xyz, si-traj.xyz, and the format is that of an extended XYZ file. So that you specify here. And then the species that your file has. If you have a more complex system, you'll have more species. Here I just have silicon. And then you can specify the size of your training data. So that's what I was talking about earlier. So I will use 80 data points for training, 20 for validation, and then the learning rate would be the step size of your training. So usually 0.05 to 0.01 works quite well. And by the way, there are comments for each of these parameters, so it shouldn't be much of a problem to understand them. And then yeah, batch size essentially means how many of these data points are processed together in a batch. And although ideally for a faster network you will want a larger batch size, but then that results in a lower accuracy. So you want to optimize this parameter as well. You can try something between like 3 to 10, I guess, and see how it affects your model. And then the validation batch size won't affect the training accuracy, but it will affect the time taken for your validation run. So you can use a as high value as your GPU allows you. And then a max epochs basically means the number of iterations for which the training will be performed. Here we'll be training it for 50 iterations, and then yeah, you can split your data set into into training and validation set randomly. And yeah, again, we will basically not go through the remaining parameters. And yeah, finally, so all this was as a string, and then I create a file called training network.yaml and put all this into that file, and then list the contents of the directory to check if the file has been created or not. And so for that, I'll do shift plus enter, and you can see that the file exists here. So this will be our config file. You can get more examples of config file in the NequIP GitHub repository. If you go here, I guess, yeah, here are more examples of the config file. And there's also a really nice tutorial on NequIP that I'd like to share with you. So I'll put a link to it in the description down below. It is by the authors themselves. And also there are a couple of really nice talks by the author themselves. So here is one of those talks where they talk about how the features rotate with geometry. So if you have a scalar feature, then it essentially changes, essentially doesn't change, so it is invariant. And if you have vector features, then you have to tell your model how they should transform under rotations, and that is done by those convolution filters that I talked about briefly earlier. And yeah, so I would really recommend that you check out these YouTube videos, and I'll put a link to those in the description down below as well. So coming back to our code, so now we have the config file, we have the trajectory file. Now we just need to train our model on those. So we'll use the command NequIP train that becomes accessible once you install NequIP, and then you specify the config file, and then you can use some options such as to enforce performing equivariance test before running the model, and also suppress warnings of unused variables in the config file. So yeah, so once we are here, we will just click on this cell and hit shift plus enter, and the training will sort of begin. You can ignore all these warnings, and yeah, here you can check whether the torch device is CUDA or CPU. It should be CUDA because we are using this Kaggle P100 GPU. So if it was CPU, it would be significantly slower. And then you can see, okay, that the data set is being processed, and then it has successfully loaded the data set. And yeah, some more energy shifts that it has determined. And then this is the equivariance test. All these errors should ideally be 0. And the training has now begun. So here you see that this is the first or the initial epoch, that is 0. And then you can see we are now, right, if we go to the end, we are now at the 4th epoch. So that can be seen actually by this, yeah. So we are in the 4th epoch, and yeah, you see a bunch of metrics being printed. It's really hard to read it right now, but later I'll show you how to read it using an Excel file. So yeah. So now I'll pause the video and wait for the training to complete. It will take some time because I am doing it for 50 epochs. Okay, so the training is now completed. It took like 232 seconds, which is not that bad. And yeah, so here you can see that it ran for 50 epochs. And now it's the time to evaluate our tester and find out how accurate the model is. So first of all, I list the contents of the directory to see what the outputs it has generated. So yeah, so let's do that, shift plus enter. So the first command, you can see, basically listed the contents of the current directory, which are these. So this is the results directory that contains our run. And since I already know that the root directory is results/si, so I just listed the contents of that root directory to see the files therein, and we can see that it also contains two more directories within that. So this is the run name that we specified, so our results are probably there. And the reason we needed to know the name of this file and like the path of this file was because next, when I'm going to evaluate the test error, I'll use the command NequIP-evaluate. Then I'll specify the training directory with this option, and then I'll have to give the path of that training run. So I'll specify the root name, that is results/si, and then the run name, and then I will specify the batch size for the training test evaluations, and then I will hit shift plus enter in this cell, and will start running the tests. So you can see right now it is loading the data, the device is queued up as it should be. Now it is running the test on those 10 frames. And here are the results, and they are really promising. So you can see that the error in the total energy is just 11 millielectron volts. However, the more commonly reported value usually is the per atom energy error, and that is below 1 millielectron volts, which is amazing. And then similarly, the errors in forces, the mean absolute error is just 14 millielectron volts per angstrom, while the RMSE is just 19 millielectron volts per angstrom, which is amazing for a model of, for a data set of this size. It was just 100 frames, and also we only trained it for like 50 epochs only. And yeah, and then finally you can deploy the model by using the NequIP deploy command and build, and then you specify the training directory as before, and then you specify the name of the model file. So here I'm naming it si-deploy.pdh. Then this model can be used to run LAMP simulations or Python like ASE molecular dynamics simulations. So that is why we deploy it like this. So, and then the next command basically lists any files with this pth extension just to see if the deployment was successful or not. So you can hit shift plus enter here as well. And yeah, so it is right now trying to deploy the model. So let's just wait for it. Yeah, so the deployment is now successful, and you can see it has listed the file with this pth extension. Now finally, since all of these computations we have done on the cloud on Kaggle, we want them on our PC to have a further look at the files and also have the model in our hands, right? So this code will help you with that. So it will help you zip the contents of the entire working directory, and then yeah, here we'll run this. So then it generates this link to the directory, and you can just click on it to download it, and it will take a few seconds to download. So essentially our working directory, we can also check how it looks by clicking over here. So here you can see all the directories that we created, the zip file that we created, the trajectory file, potential file. You can also check the contents of the results directory from here as well. So yeah, so the download I think is complete. So let's open it. So it's like 26 megabytes. So here we are in Kaggle, then we are in working, and yeah, so here is the results directory, then the SI directory, and then the run directory. And here are some of the important files that you will like. So you would like to see the, let's say, the metrics as your model evolves. So you will open this file called metrics epoch, and this is a CSV file, so it can open in Excel, and then you can plot the error in training as well as validation, and then observe how it changes throughout. So here we have the validation error in energy per atom across all the epochs. So there will be 50 values here. So you can see there are just 50 values, and then I'll create a plot of those to see how it changes throughout the iterations. So yeah, so you can see during the initial epochs the error reduced substantially, while for the remaining epochs it sort of plateaued. So yeah, so this is useful for your papers or something, or to monitor your model, like how the errors are progressing. So I think that was mainly it. You can also check out the remaining files as well. So yeah, so I think that's it for this tutorial. I hope I was successful in giving you first-hand knowledge on how to train your own machine learning model using the NequIP library. And in case you guys found this tutorial useful and helpful, then don't forget to hit the like button and subscribe to my channel for more videos like this. If you have any questions or doubts, you can leave them in the comment section down below. Thanks for watching and have a great day.